So, as I said, we are going to work with the previous dataset about the data preparation or data manipulation, okay? If you remember, we were working with the Titanic dataset in which we could find, if you remember, the passenger ID, the survived, which indicates if a passenger survived or not. Also, if you remember, this is the class, the target class that we want to classify, the passenger class, first, second, third, the name, sex, age, siblings and spouses, parents and children, ticket number, the fare, the cabin, and the port in which the passenger embarked. Okay, we perform several transformations over this dataset. Firstly, we looked for missing values. We could see that here we had age, cabin, and embarked with features with missing values. Okay, so first of all, here, okay, we removed some variables that were not relevant, the name, the ticket number, the cabin, and so on. Then we had this data frame, but what we had to do is to separate the data frame in two different data frames. A categorical, a data frame with the categorical features, and another data frame with the numerical features. Okay, so here we split it, and here we have the categorical one. When I have to re-execute everything, be careful. It's sometimes it's a source of errors. If you don't re-execute all the cells of the data of the notebook, it will not work. Okay, so let's do it. Well, this is not necessary, but I'll re-execute it. The pop. Here we have the data frame printed, the split up in numerical and categorical, the categorical data frame. Here we used a simple imputer to impute missing values. Okay, in the categorical columns, we can impute them as the mode or the most frequent one. Now we see that there are no missing values. And we also saw that we needed to transform the columns into numerical features, okay? First of all, we used a label encoder, which might be useful for the sex column, but not for embark, because we are introducing an order that is not present in the data set, okay? I don't know if I executed this cell. No. Okay. But we presented another approach, which was to use a one-hot encoder for the envar feature, okay? Having these variables, the sex male, indicating if the passenger was a man or a woman, and the port in which the passenger embarked, indicating in this case, for instance, that the first passenger embarked in Southampton and not in the other ports. Okay, then treating the numerical variables, we imputed the mean. We imputed the missing values with the mean. We could use, for instance, also the median or even the mode. Okay? It's not very common to impute by the mode in numerical cases, but you can do it. Okay, now we see that we have not missing values, and we merge both data frames in just one. And this is the last thing that we saw, that was to select a subset of relevant features, okay? Here we saw that using the chi-squared method with having only 4 target variables to remain, it was selecting the sex, the class, the age, and the fare, okay? So this is what we have, and we can also select another criterion, which is the mutual information. Okay, mutual information. We see that it still remains sex, but in this case, it chooses one of the ports in which the passenger embarked. Or we have again the class, and we have the fare, but be careful here, we don't have the age. And it seems that the age might be relevant, but in this case, it doesn't choose the age. Okay, so here we were in the previous session. Any doubt that you would add, that you would like to ask? Okay, you also have all the steps. Sorry, you also have all the steps in the slides that you have on Moodle. Okay, yes.
Is there some randomness in the process of selecting the feature? Because in my final dataset, I have the age feature.
You sorry, I can't hear you very well. You don't have the age where here?
No. I was just asking if there is randomness in the process that selects the final feature.
No, I can't hear you. I don't know why, but it's very like metallic, the voice.
Okay, it's okay though. Don't worry, it's not important.
It's okay. And anyway, if you would like to write anyway.
I have another question.
Yes.
Could you please explain why you would go for the one hot encoder on the embarked variable rather than just label encoder?
Yeah. Well, let me show the slide. Okay, the simple imputer transforms categorical variables into numerical ones, but assigning, for instance, if we have three different ports, I think they were M, S, and C, it assigns, for instance, 0, 1, and 2 for the three ports. Okay? This is explained. Okay, it's here. The problem by doing this is that we are introducing an order. It means, for instance, let me draw. If we have three different ports, which are, I'm not sure if they were these ones, but okay, anyway. The ports were C, M, and S, okay? And what it does, the label encoder, what does is to assign 0 to the C, 1 to the M, and 2 to the S. Okay? If we see here, we don't have an order of precedence. Well, you may say, okay, we have an alphabetical order, but actually the meaning of the ports doesn't introduce an order because we have this port, and this port, okay? And when we assign these values, now we have an order, okay? An order that was not desired to have. So we have a problem because we're introducing an order where there wasn't an order. Now we say that S is greater than M, and it has no sense at all. Okay, so what we do is to say, okay, instead of doing this, let's have three different columns, three different features, C, M, and S. And if a port was C, I will say 1 here, 0 here, 0 here. If the port was M, I will have 0, 1, 0, and if the port was S, I will have 0, 0, 1. By doing this, we are not introducing any order, okay?
So if there is an order encoder, like small, medium, large, would you go for the hot encoded? No, I mean, like, would you go for the label rather than hot encode?
Yeah.
Oh, right. Thank you.
Yeah. For instance, imagine that because it all depends on the meaning of the variables. That's very important. That is why it is very important to have a complete understanding of the data. Okay. Imagine that the classes in the passengers are encoded like in the dataset, like first, second, and third, with letters. Okay. Then it is correct to use a label encoder because actually first comes before second and second comes before third. Okay.
Okay.
It all depends on the meaning of the variable. Okay, Elias asks, is there randomness in the feature selection process because my dataset keeps the 8th feature at the end? I just realized when you launch again the last cell, the selected features used to change. So there should be some, maybe there is some randomness. I don't know at which point. In fact, when using scikit-learn, you have some randomnesses that are not actually present in the original algorithms. For instance, when you build a decision tree, there should not be any randomness. Okay, there should not. But the implementation of the decision tree in scikit-learn, we have some kind of randomness. Actually, I don't know where it comes from. Okay, well, maybe I can guess that it's a way to accelerate the process because it is also thought for large data sets with many features and many rows. Okay, so the original algorithms should not be random. Should have not any kind of randomness, but when we're working with scikit-learn, maybe because of optimizations, it selects maybe features using a random choice or something like that. Okay, not sure why, but it is possible, of course. It is possible. Okay, let me re-execute. If I re-execute this, for instance, sex, embark, class, and fair. Sex, class, part. Yes, it is changing, of course. So there might be some randomness. Yep. Maybe, let's say, your random state equals to 1. No, it doesn't work here. Or maybe the name is a different one. Okay. Okay. Then that's it for decision trees. You can put sit in. Well, yes, maybe it's because let me look for it. Maybe the number of the parameter is different. Okay, let me. Because sometimes the names are a mess. No, actually, the only 2 parameters that you can specify is the method and the number of variables. You cannot specify a seed. Oh. No reference to random guesses in the documentation. But of course, there might be some kind of randomness. Okay, any other question that you would like to ask? No? Okay, so let's continue. Okay. Maybe you have noted that we have still one missing a step, because we saw how to pre-process our data, how to explore it, how to explore the data, how to pre-process the data, and then you want with Alejandro to deploy the models. But we still have to see how to learn a model, okay? That is what we are going to see today. Well, I still have to see the last part of this presentation. Let me show it to you. Okay, so we were here. And let's see how to discretize our data. Okay, you may say, okay, you have said that we need everything in a numerical way. Why would you like to discretize? Okay, some algorithms work much better with these discrete features. That doesn't mean that internally they are not encoded with numbers, okay? Because of course we will see that what we are going to have are one-hot encoding features for each discretized feature, okay? So for this we are going to use a k-bins discretizer. K-bins discretizer, what it does is to split the range of our feature in intervals in which all the intervals contains the same number of samples. See, you can see that here this is a criterion, but we could use another criterion. Maybe we could select the criterion of splitting the algorithm splitting the interval in subintervals of the same size. Okay, we could do that as well, but it has more sense to split the whole interval, our range, into intervals, including each of them the same number of samples. Okay, so by doing this, you can imagine that all the subintervals do not have the same size. Okay, we have a parameter which is the number of bins, the k. This is not ideal. Personally, I like more another algorithm in which you don't need to give the number of bins, which is the Fayad-Tanirani algorithm. But while this algorithm is non-supervised, okay, you can also apply the definition of supervised and unsupervised learning to these algorithms. This algorithm is not supervised because you only take each column independently. Okay, you take, for instance, the fare that the passenger paid. Okay, if you have the fare, you only need the fare because all you have to do is to put the same number of samples in its subinterval. But the other algorithm, the Fayad-Tanirani algorithm that I say, is supervised in the sense that it also needs the target variable. Okay, in this case, it would need the supervised variable, and it chooses the splitting points of the intervals by maximizing the exchange of information between each subinterval. For instance, here, if we have here that in this interval all the classes are 1 and here all the classes are 0, then I will choose here a splitting point. Okay, so it tends to split the interval, but trying to separate as far as possible the target variable, okay, the class. But unfortunately, this algorithm is not implemented here in scikit-learn. Okay, it is implemented in other tools like Weka. I don't know if you know Weka. Any of you know Weka? Yes. So that algorithm is implemented in Weka, okay? So how to do this in Python? Okay. All you have to say is here once again it's the same as all the time, okay? K beans discretizer, number of beans 5, and I also say that I want to encode it as one hot encoding in the dense format for the matrix, okay? And transform it and put it into a data frame, okay? I've called the discretizer a binner, and I called fit and transform, okay? I learned the splitting of the intervals, and I transform the whole interval. I'm dropping here some classes that are not appropriate to discretize. Sorry. Because, for example, the class, it has no much sense to discretize the class because it's already a discrete variable. These variables are already discrete. Okay, they are integers, so they are discrete. And we are discretizing, for example, the fair and so on, okay, because we are discretizing the numerical data frame. Okay, I'm not going to do it because actually we are not going to use it, but just for you to know. And sometimes we need to scale our features. Why? Because some algorithms need the features to be in the same scale. We will see that SVM algorithms need the features to be in the same scale. Okay. With a min-max scalar, we can transform our interval, the whole range of a numerical variable, into, how do we select the number of bins? Well, the number of bins is a parameter that you have to adjust, trial and error. Okay, there are more formal ways to adjust a parameter, but here, trial and error. Okay, you can try with 3 bins, with 5, 4, 6. I wouldn't go for more than 10, but sometimes it happens. Okay, that the best number is more than 10, but no much more, no many more than 10. Okay, actually 10 is more than enough. Okay, be careful because if you select too many bins, you will overfit. Okay. Sorry. So with min-max scalar, we can transform the range of our feature to the interval 0, 1. Okay, the minimum will go to 0, sorry, and the maximum will go to 1, and all the values in the middle will fit a linear progression. Okay, a linear regression. We can also specify another range, but 0, 1 is the most usual one. For transforming our data with the scalar, we do exactly the same. Here, min-max scalar. Here we could say another range, but 0, 1 is more than okay. And we call the method fit transform, also for the same variables as before. Okay. And for instance, here we have the transform. Well, it is not in a data frame. We could put it into a data frame, but we have not. We have 2 variables because after removing class, siblings and spouses, and parents and children, we only have 2: the fair and other one that I don't remember, the age, the fair and the age. Yes. And instead of having ages of 30, 40, or whatever, you see that we have everything between 0 and 1, and the same for the fair. Okay. We can also use a standard scalar. Okay? With a standard scalar, the kind of normalization is not the same. In this case, it's a normalization, not a scaling. Okay. With the normalization, what we do is to subtract the mean and divide by the standard deviation or the standard error. Okay, it's like when we want to transfer any data to a normal of mean 0 and a standard deviation of 1. Okay, it's the same, but in this case we have to say standard scalar here. And in this case, as you may see, here we have negative values, and we don't have like a like a maximum value or a minimum value, because actually the maximum might be 1, 2, 3. It depends on how far from the mean the farthest value is. Okay, and of course, more or less the half of the values will be negative and the other half will be positive. Okay, this is used if we know that a variable follows a normal distribution, but that is not that common. So mainly we will use this scalar. Okay, if we know that a feature follows a normal distribution, we can do this, but it's not that common. Well, actually, normal variables are present. They are there in the environment and so on. Okay, for instance, if we have the sorry, if we have the heights of different people, they follow a normal distribution, so we could use this kind of scalar. Okay, so that is what I wanted to tell to you, still from the data manipulation, and let's move into model learning. Okay, okay, as I said before, we are going to work with the Titanic dataset. We are going to take as starting point the data frame, which is called data frame preprocessed. Okay, if we go to the notebook, df preprocessed, this one, which is already ready for the model learning. Okay, so first thing that we need to do to divide our dataset in two folds: training and testing. You know that we cannot validate or we cannot test our model with the same samples that we are training. So what we are going to do is to divide our dataset into two folds. Okay. For doing that, in scikit-learn, we have a function that already does that. Okay. Here we have to say from scikit-learn.model selection, you have to import train test split. This function is quite curious because it returns four different variables. Okay, it will return in the first position the predicting variables of the training set, then the predicting variables of the testing set, then the target, the class variable of the training set, and then the class variable of the testing set. The parameters are, first of all, the data frame with the variables for prediction, then the class. Okay, you see that we have to give them in separate parameters: the predicting variables and the variable to be predicted, and it returns them also in different variables. The testing size, the size of the testing fold, in this case we say that the testing fold must contain the 30% of the samples. We can also say here training size, or training size, and we can also give an integer number, which in that case it means that they are in absolute terms, but that that is not that common. Okay, the most common thing is to give a proportion. Okay, in this case, we say that we will have 70% for learning and 30% for testing. And of course, so that everybody obtains the same results, we can select the same random seed or random state, saying that one, and we can print, for instance, the xtrain, the breakthrough variables of the training set. So let's write this into the notebook. Here, okay. So we can say, okay, you can follow me from scikit-learn dot model selection import train test split. I will copy the name of the function, and I will say I will have 4 different variables: xtrain, xtest, ytrain, ytest, and function which is first parameter is the data frame. The second one is the class column. The third one is the test size, for instance, 30%. And finally, we can state the same seed so that everybody obtains the same. And here we can print, for instance, the training part, the training fold. Okay, you see that the rows are not in the same order as in the beginning. Okay, we have a random order now. If you see here, we have 623 rows, while in the original dataset we have 891. Okay, if we make this, oh sorry, this, well, actually it's times 0.7. You see that, well, it rounds to the floor value. It's not an actual rounding, but taking the floor. Okay. So this is the first thing that we always need to do. Divide our dataset into training and testing folds. Okay, and we are going to learn with training, and we are going to test our result with the testing fold. Okay, and this is what we obtain. First of all, we are going to start by learning a decision tree. How to learn a decision tree is very, very easy. All we have to do is to declare the algorithm that we are going to use, even if it is a decision tree, an SVM, a random forest, a KNN, or whatever. Okay, and then we call the method fit with the training dataset. Okay, in this case, well, you see that here we have some parameters for the decision tree. First of all, we are not going to include any parameter. We are going just to train a decision tree classifier. Okay, you see that you have the decision tree classifier in scikit-learn.tree. So from scikit-learn.tree, import the decision tree classifier. We are going to learn a decision tree. So from scikit-learn.tree, import decision tree classifier. I'm going to copy this. Okay, this will be a tree. By just doing this, we can learn. We are like initializing our tree. And we can train the tree as easy as doing this. Tree.fit, and here we have to give the predicting variables and the class. So we are going to use this training set and the classes of the training set. By doing this, we already have a decision tree learned. We are ready to make predictions. Okay. Anyway, so that everybody learn the same decision tree, we are going to include here the random state, the seed, okay, because otherwise each person will obtain a different result. Okay, and how to make predictions? It's very easy. We call tree.predict, tree.predict, and we want to predict, in this case, with the testing fold. So xtest. And the predictions are 1, 0, 1, 1, 1, 0, 0, etc. Okay, survive, not survive, 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 not survive, not survive, and so on. We are going to keep these predictions a new variable, ypred. And now we can see, we can print the actual values, the values that should be predicted and the values that we have predicted. Okay, we see that for this passenger, he or she survived, and this is the actual, okay, decision test. And the classifier says that survived. Perfect. Not survived, not survived. Sorry. Survive, survive. Here we have an error. The class, the actual, actually it didn't survive, but the classifier says that it survived, which is not correct. Okay, so here we have a classification error. But how to perform this more formally? Okay, how to see if a passenger survived or not more formally than just, well, we can compare them, but we have tools that make it easier, okay? We will see these parameters later. Well, here we have the predict. Okay, this is what we have just obtained. And what we can do is to obtain the confusion matrix. Okay. For doing this, we have to take into account that scikit-learn sorts the labels in alphabetical order. So if our labels are 0 and 1, alphabetically talking, which means actually in the ASCII code, 0 comes before 1, which is also the usual definition, okay? But for instance, if we want to predict between survived and not survived, okay, imagine that our labels are survived and not survived. Then not survived is before survived because N comes before than S in alphabetical order. So we can call the confusion matrix method, which is in scikit-learn.metrics, giving as first parameter the actual values and as the second parameter the predicted values. But confusion matrix returns a matrix of a NumPy matrix. Okay, we would like to make it more elegant. We can put it in a data frame, giving names to the columns and to the rows by specifying the index, saying that, okay, also be careful, in the columns we have predictions and in the rows we have actual values. So the columns will be, the first column will be the values predicted as 0. The second column will be the values predicted as 1. The first row will be the values whose actual value is 0, the samples whose actual value is 0, and the values whose actual value is 1. Okay, obtaining something like this. So let's implement this. So here, let's obtain the results in a different cell, okay? Well, not in the same cell, actually. From scikit-learn dot metrics, we are going to import the function confusion matrix. Okay, I can just call confusion matrix given y test and y print. Okay, well, I don't want these prints anymore. If you see here, we have a matrix, but it does not say, for when we want to present our data, it does not say if the rows are the actual values or if the columns are the actual values. It does not say which are the labels and so on. So we would like to put it into a data frame. Well, just doing this has no much sense. Well, in this case, the 0 and 1 are the same, but if the labels would be survived and not survived, the labels would still be 0 and 1. Okay. So what we have to do is to give a name for the columns, predict 0 and predict 1, and index through 0 through 1. Okay, and we can even store it in a variable. Okay. So this is what we have here. And we can also obtain the metrics calling the classification report. Okay, we can import the classification report function from the same module. Here we can import classification report. And here we can print it. Print classification report of the same, the actual values and the predictions. And we obtain this. Okay, if you remember, because I think that, I don't know if Ernestina or Alejandro already gave you some, well, or maybe in other courses, because I'm not sure, okay, in other courses of the master. Okay, here you have different metrics. The most important one might be the accuracy. We see that in this case, we have an accuracy of 75%, which indicates that the 75% of our samples are correctly classified by our classifier. Okay, it's not bad, but it's not the best value. Also, we have precision, recall, and F1 score. Okay, precision, recall, and F1 score depends on your definition of positive. In this case, we might consider, for instance, that a positive value is 1, having that the passenger survived. That is our positive. So in that case, having 1 as positive, the precision is 0.75, the recall is 0.63, and the F1 score is 0.69. And we have a total of 115 samples which belong to the class 1. If we consider that the positive is that the passenger died, then the precision is 0.75, the recall is 0.84, and the F1 score is 0.8, having 153 samples. We can have an average of both cases, and in this case, of course, the weighted average is the average taking into account that here we have 153 samples and here we have 115. Okay, so it's this times this plus this times this divided by the total, that is this. If we consider the macro average, it's just the average of the two values, okay? In almost all the cases, the values are pretty similar, okay? In these cases, because the classes are balanced. Okay, I'm sorry if I don't give more details about this and how to interpret this, but I think that you already know something about this, okay? Because I don't know if in this course or in other courses you have you should have learned about them, okay? Is that correct? Have you learned about these values before? Okay, perfect. They can be obtained from the confusion matrix, okay? Having the confusion matrix, we have everything. So, this is what we obtain. Well, depending on the application, we should focus more on the recall or on in the precision. In this case, for instance, as it doesn't matter if the errors are here or are here, we are just going to see the accuracy. Okay, so we are obtaining a 75% of accuracy, which is not bad, but it's not good, as I said before. Okay, so let's modify some parameters here. Okay, we have a decision tree which might be overfitting. Okay, because if you know, because I think that you have also learned something about decision trees in other courses. Decision trees tend to overfit data to the tend to overfit the model to the data, because we have branches that are very deep. So we can restrict this by, for instance, giving a max depth attribute. Well, I think it's called max depth. Yes, for instance, we can say max depth equals to 3. Well, I'm going to limit it to 5 or to 4. Here we see that it improves a little bit the accuracy, having a maximum depth of 4. Okay, a maximum depth of 4, it means that the decision tree, for instance, well, let's put the example with 2. Okay, this might be our decision tree. If the max depth attribute says 2, it means that we cannot go deeper than this. This is the limit. Okay, if we specify a max depth of 1, it means that this is the limit, so these nodes will be pruned. Okay, and this way we can sometimes make it better. Well, it's not always better, but we tend to evit the overfitting. Okay, we can skip the overfitting by doing this. Also, we have more parameters here. For instance, mean samples split. Okay, it means that if I don't have at least 5 samples in the current node of the tree, I will not split, even if all the samples are not correctly classified in this node. Okay, so but because having less than 5 samples, it means that if I have 4 samples and they are not perfectly classified, all of them, what I'm going to do is to overfit to our data. We are going to learn from the noise. So we want to, we wouldn't like that to happen, okay? So here we can say min samples split equals to 5. Okay, I don't know if we have had changes. Maybe not. No, the results are exactly the same. And we can also limit the number of samples in a leaf, saying that if we don't have at least 3 samples in a leaf, don't split. Okay, so here min samples leaf equal to 3. Is it correct? Yes. Well, I don't know if the results change, but okay. These are options to prune our tree. Okay, to take them into account. So these are with the trees. I have taught you how to split our data set, how to do the fit and predict method, how to build the classification report, how to build the confusion matrix. But now we can use also other models. Do you want to ask anything about trees? We can also draw the trees, but as we don't have much time, I'm not going to go into this. Anything that you would like to ask about decision trees and how to implement them or how to use them, the implementation? No? Shall I continue then? Okay. Is it good? Okay, stop asks. Is it good to use it for regressions? To use what? Decision trees? I think that there are methods which are called the regression trees. Okay, not exactly the same because, of course, decision trees are for classification. We are going to focus on classification problems. Okay, I think that you have regression trees for regression, but not the same trees. Okay, let me. Okay, yes. Actually, in scikit-learn, it's called decision tree regressor. Okay, and in this case, it can be used for regression. But be careful because in regression problems, the whole problem is quite different. Okay, because here you have to select the criterion if you want to minimize the mean square error or the Friedman mean square error or the mean absolute error. Okay, the splitter, I don't know what is the meaning of the splitter here. You still have things like this, okay, but they are quite different. And of course, the metrics that you are going to use to evaluate a regression problem are not the same. You don't have a classification matrix in a regression problem. You have to evaluate the mean absolute error or the mean square error. Okay. Okay, but you have this, the efficient tree regressor. Okay, anything else? No? Okay, so let's continue. Other models. For instance, we can use ensemble learning. Ensemble learning consists on learning multiple models to solve a problem. Well, sorry, because it says problema here. Let me change it. The corrector, it detects that my office is in Spanish and it tries to correct me when I'm writing. Okay, so we learn several models. There are two types of algorithms. In fact, there is a third one, which are called the stacking algorithms, but they are like more advanced, and we are not going to talk about them today. So, consider an algorithm. This is the best situation in which we have a low variance and low bias. Okay, this means that all the different, if we learn the same model or the same kind of model with different data, for instance, selecting a different subset or something like that, low variance means that the model will be very similar learning the model with a different subset of data or something like that, or introducing more data, okay? And the bias indicates that the classifier actually works well, okay? If we have high variance but low bias, it means that, for instance, decision trees are here, okay? It means that in average, it is okay, the classification trees works well. But there is a very high variance. If we modify the learning set, the learning data set, or the learning fold, we may be here or here. If we make another modification, we might be here. With another modification, we might be here. And it does not need to be a very big modification of the dataset. Okay, maybe just introducing 3-4 samples, the final result might be very different. So this is why we say that decision trees are unstable classifiers. Okay, if we are here, it means that all the classifiers will be very similar, but they will not work well. Okay. If we learn a decision tree, a very naive decision tree, we will be here. Okay. With decision trees that are very easy, the features selected in the root of the tree will be all the time the same. So we will not have that variance, that high variance. But as they are very simple trees, they will not predict very well. So we will be here in that case. And here we have like the worst situation in which the classifiers are not correct and a simple perturbation in the data makes that the final model is very different. Okay, so the technique that we have with ensemble learning, bugging. The bugging algorithms allow to decrease the variance with little impact in the bias. Okay, so with a bugging algorithm, we may help a decision tree to get more stable, to stabilize decision trees. And boosting algorithms. Boosting algorithms allow to decrease the bias with a little impact in the variance. With boosting, we might fix this situation. Okay, this, for instance, those very simple trees, which all of them are pretty similar, we may move these points to here. Okay. Today we are only going to see this case, the bugging algorithm, which is random forest, which is very common classifier. We don't have time to focus on boosting algorithms. Here we have AdaBoost classifier. Okay, it's very easy to use, but as I would like to explain it in a more detailed situation, I'm not going to use it. Okay, so bugging. In bugging, what we do is to divide our dataset in different subdatasets, but be careful because actually this subdataset does not need to be exclusive between them. So this means that, for instance, imagine that here we have the 30% of the samples. It doesn't mean that if, and this is also a 30%, 30%, 30%. If we have a sample here, we may also have the sample here or whatever, okay? Every time that we build a new sub dataset, a new bootstrapped dataset, we replace the samples. It's with replacement, okay? Then with each subdataset, we learn a classifier, and each classifier will make a prediction. Each classifier will get its own class, its own prediction for the class. C1, C2, CT. Then the ensemble algorithm, the bugging algorithm in this case, what says is to take what the majority says. Okay, as easy as that. Take the majority class. Bugging helps to establish unstable algorithms like decision trees or neural networks. Be careful. For instance, KNN is an unstable classifier. Okay, it's not unstable. The most representative algorithm here is random forest. Okay, it's the most extended bugging algorithm. Random forest constructs many decision trees at training time, and the output is the mode of the class. Is the class that most of the trees said that is the correct solution. Algorithm. Okay, you have to repeat until you reach the number of trees that you want. The number of trees is a parameter of the, well, actually it's a hyperparameter of the algorithm. Maybe a good number might be 100. Okay, so what you have to do is to bootstrap the dataset. Okay, for instance, for each of the trees, you have to select the 30% of the samples, or the 50%, or the 70%, or the 10%. Is a parameter as well. Okay. You also have to select a fixed percentage of features randomly. If you see, this is like a double bugging operation. Not only the samples, but also the features. Why we also select a percentage of the features? Because the decision trees, as I said before, tend to have the same root. So if we have the same root, maybe we might have similar trees at some point. To avoid that, and so that we have very different trees, we are also going to select the features randomly. Well, in this case, we might have some trees which are very bad, but it's not important because all the other trees which are good will compensate the trees that are bad. Okay, and then we have to train a classification tree or a decision tree, more than a classification tree, for the resulting dataset. Okay, the best feature of random trees is that they are robust to overfitting when the number of trees is high enough. Okay, 100 or 50 or even 50. Okay, problem, it gets really challenging to understand the model. Okay, in a decision tree is very explainable. Sometimes we have to cope with the fact that we have to explain the models to our bosses, and that is not easy with decision tree. With decision trees. Okay, with random forest. It is easy with decision trees because it's like a. Can you hear me? No. Can you hear me now? Can you hear me now?
Yes.
Okay, sorry. I had a connection. Sorry. Well, random forests are robust to overfitting. Okay, but as I was saying, the problem is to try to explain the model to our boss. Okay, decision trees are easy to explain because you can say, okay, do you see this variable? Okay, if this variable is greater than this, then go to here. If this other variable is greater than this, go to here, and so on. Okay, they are easy to understand, but the model here is not that easy, and the boss have to to trust in a black box. Okay, so how to learn a decision random forest classifier? It's very easy. Random forest classifier is the same as before, but now we have to change here to random. Well, we have to import the random forest classifier from scalar.ensemble instead of .3, and here we say random forest classifier, the number of estimators, and that's it. Okay, we can also give some parameters about the trees, like the max depth and so on, but this is not that common in random forest. We can do that, but it's not that common. Let's implement it. To implement it, I'll copy this. Here I will say from scalar.ensemble import random forest classifier. Okay, the name of the parameter is n estimators. It's the number of trees. N estimators, like 100. Random state 1. Okay. I'm going to rename it like RF, random forest. Change it here, and we change it here. And now we see that we obtain a 76% of accuracy. But if we see, okay, the accuracy is pretty similar, but here we had 57, and here the recall is not that bad. In fact, we don't have so bad numbers. The lowest number here in these metrics is 62, while here it was 57. While we had here 93, and we don't have 93. Okay, so it all depends on our purpose. It all depends on our purpose. Okay, anything that you want to ask about decision trees? Sorry, about random forest. I don't know if there are more parameters here. No, because actually we can modify more parameters, but we are not going to talk about them. We can modify because I have not said how to modify the number of samples or how to modify the number of features to include, but it's more than enough with this. If you want to investigate more, you have the documentation of scikit-learn, okay? But we will not ask more than this. Okay, SVM. In SVM, we have to treat the dataset as a numerical structure, as a subset of Rn times C, okay? Like a subset of an Euclidean space of dimension n and the class. Okay, it's Euclidean space of dimension n, Fn and the class, and the class, of course. SVMs, which means super vector machines. here we have a question. Do you know when we will have information about future student projects step? I don't know. You mean about the second assignment that you have to prepare? Yes, today. That's the reason why I'm going a little bit fast, because I will give you your assignment today, okay? And you will have to deliver it. I think that on January. In January, sorry. Okay. Yeah, no problem. So SVMs. SVMs try to learn a hyperplane in the Euclidean space that divides the samples as much as possible. So imagine that we have two classes, blue and red. So it tries to learn a hyperplane. A hyperplane is a subspace of the dimension n-1. In the case that we are working on a plane, it's a line, okay? In the case that we are working in a three-dimensional space, it will be a plane and so on. And what SVM tries to do is to do this, to split the space in two subspaces and leave the blues or the blue samples on one side and the red samples on the other side. Sometimes this is not possible. Well, sometimes no. Always it is not possible. In real applications, we will have here some samples which cannot be correctly classified. The SVM classifiers can still cope with that. Okay, they treat those cases as errors, and they can learn a good hyperplane. For that, it has the C parameter which weights the errors. Okay, we are not going to go deeper into the algorithm. It's a very mathematical algorithm. You can do this to learn. It's very simple. From scikit-learn.svm import svc, supervector classifier. Okay. So let's copy it. Here from scikit-learn.svm import svc. Here svc, the parameter is c. We don't have random state here. We can call this for instance svm, and we see here that the accuracy decreases to 68%. Okay. Why? Because the features are not in the same scale. Okay. Here, having features in the scale of thousands, I think for the fair makes, because actually when we have in a scale of thousands, imagine the feature in that scale is much more important than the feature in the scale of a tenth. Okay, for instance, the age. Okay, the fair is much more important than the fair, because the fair is has a scale of 1,000, 2,000. It has very big differences, while the age, the differences in the age compared to the differences in the fair is not that big. Okay, so what we have to do is to scale the data with a scalar. Okay, we have to import the min-max scalar. We initialize it. Here, if you see, we put again into a data frame, transform the data. We assign the name of the columns and the indices. But be careful, because this has to be done with the numerical data frame. Okay, so let's do it, because of course we cannot scale variables that are not numerical. by default. Let's do it. Okay, here I am going to say from scikit-learn dot preprocessing import min max scalar. I'm going to initialize the min max scalar. Okay, and in this notebook I have already defined the numerical part of the data frame, and I'm going to define now the numerical part scale. Okay, I can just call the min max scalar dot fit transform the numerical data frame. Okay, be careful, because by just doing this we will lose the numbers or the names of the rows. So if we don't want to lose this information, we have to put them into a data frame and the name of the columns okay, and the name of the rows, like this. And now we can merge this data frame with the categorical one. Preprocessed, calling it preprocessed again, but in this case we are going to merge in the left side the categorical with one hot encoding, and in the right side the numerical but scale. And using as criterion to merge them the passenger ID. Okay. Now we have to split this data frame again into training and testing, because of course they are different. Okay, so I'm going to I'm going to copy. We have the splitting here. But instead of preprocessed, I'm going to call this scaled, preprocessed scaled, and I'm going to use the preprocessed scale. The class column is the same one, and not to lose the previous steps, I'm going to call all these ones scale. Okay, and when I fit this, I'm going to do this with the scale data frame. Well, okay, there is an error where here columns. Something is not working, maybe. This is strange, because actually it should not be a perfect classification. Let me check what happens. quite strange that we have a 100% of accuracy. Hmm. Okay, something happens and I don't know what's happening. Okay, but the result should not be that good because actually it should be something like this. Yes, but actually it seems that it works. No. No. Oh, yeah, I know. I think that I already know. Yes, it seems that it works perfectly, but I don't know why. No. Well, something is happening and I don't realize what. Yes, I'm going to continue because I don't know why is this happening. Okay, it's very strange that it is so perfect. Anyway, I will continue. Another classifier is the naive bayes classifier. Okay, it is a probabilistic classifier which calculates the posterior probability of each label of the class given the set of observations that we have. Okay, it makes use of the Bayes theorem, which is this one, but making some assumption because otherwise we could have very big tables, which is not efficient nor neither in storage nor in computation. Actually, it could be it could have an efficiency, an exponential complexity. Okay, so it would not be a good idea. Actually, if we use the whole Bayes theorem, what we could have are Bayesian networks. But we don't want to work with full Bayesian networks. We want just a simple classifier. Okay, so naive Bayes classifiers make an assumption, an important assumption, which is that all the features are conditionally independent of each other when the value of the class is known. Okay, in this case, we can simplify the formula like this: the probability of the class times the probability of each class of each feature given the class. Okay, and omitting the denominator because it's just a normalization between all the labels of the class. Well, to learn the classifier, if we think that the variables follow a Gaussian distribution, we can use a Gaussian naive Bayes, like this one, okay? And it's the same as we have been doing. It's just Gaussian naive Bayes, and we do the fit and the predict, and so on, okay? I'm not going to stop because, of course, I prefer to finish with this because I still have to give you your assignment. But are we sure that the features follow a normal distribution? That is not that is not actually happening. Okay. In that case, we have to discretize and use with a k-bins discretizer, and then well, we have to do everything again because we have to discretize the variables that are continuous. Okay. Then we do this again. We separate into training and split in the discrete dataset, and we can use the multinomial naive Bayes classifier. Of course, you don't need to do the discretization process by hand. You can leave the decision to the multinomial naive Bayes. You don't. In that case, it's as easy as in this case. Okay, you can change here by multinomial naive Bayes, and it will decide the best number of bins for each feature, or the number of bins that it thinks that it's the best one. Okay, but if you want to give your own number of bins, you have to do this. Otherwise, just by changing here Gaussian by multinomial, it will be enough. Okay. Oh, sorry. And learning with multinomial, it's the same. Okay, it's just fit, predict, and obtain the metrics, and that's it. Okay. Anything that you want to ask? No? Well, in that case, I will stop the recording here, and I'll start another recording for the assignment so that you have it in different videos. Okay, so that way it will be easier for you if you want to rewatch the video about the assignment or whatever. Okay, let me stop the recording.